All right, let's talk about microcontrollers. We all know they're basically the brains of any electronics project. They can think, they can calculate, they can make decisions. But there's a catch. By itself, a microcontroller is kind of like a brain in a jar. It's super powerful, but totally isolated. To do anything cool, it has to talk to the outside world. It needs to read sensors, control motors, and chat with other devices. So in this explainer, we're going to pull back the curtain on the secret languages these tiny brains use to speak and listen, the wired communication protocols.
So here's the game plan. We're going to start with the absolute basic idea of sending data one little bit at a time. Then we'll jump into the big three protocols you'll see everywhere: UART, I²C, and SPI. And to wrap it all up, we'll see how these languages let our microcontroller actually connect with sensors and, understand the world around it. So this is it. This is the big question we're tackling. You've got this awesome chip, an Arduino, an ESP32, whatever you're working with. It can run all this complex code, but how in the world does it get the temperature from a sensor or tell a screen what to display? Well, the answer is that the devices have to agree on a set of rules for talking. They need a protocol.
Okay, let's get into it. Before we learn the specific languages like UART or I²C, we've got to understand the basic grammar they're all built on. And the most fundamental way to get digital info from point A to point B is with something called serial communication. Think about it like this. Serial communication is like a single-lane country road. The cars, or in our case, data bits, have to go one by one in a single-file line. It's simple, it's cheap, and it works really well over longer distances. Now, parallel communication, that's like a massive 8-lane superhighway. You can send 8 bits, a whole byte of data, all at the same time. It's way faster for sure, but it needs a ton more wires, it's more complex, and it's really only good for short trips. For most of what we do with microcontrollers, that simple country road is perfect.
So let's move on to our first specific protocol. This is probably the one you'll run into first. It's called UART. And if serial communication is the general idea of talking, you can think of UART as a specific dialect. It's like a direct, one-on-one phone call between two devices. Super straightforward.
UART stands for Universal Asynchronous Receiver Transmitter. Universal because tons of things use it, but the real key word there is asynchronous. What that means is there's no separate wire sending out a beat, a clock signal, to keep both devices perfectly in sync. So how do they not get confused? Well, they agree on a speed beforehand, that's the baud rate, and then they wrap every single byte of data with a start bit and a stop bit. It's kind of like yelling, "Hey, listen up," before you talk, and "I'm done" when you finish.
And here's the thing, if you have ever used the serial monitor in the Arduino IDE to see messages from your board, you've already used UART. That's it right there. The connection is dead simple. It's just 2 wires. The transmit pin, TX, of one device crosses over to the receive pin, RX, of the other, and vice versa. So device 1 talks into device 2's ear, and device 2 talks back into device 1's ear. That's all there is to it. So let's zoom in and look at what's actually happening on that wire. This diagram shows exactly how 1 byte gets sent. Normally, when nothing's happening, the line is held in a high voltage state. To start talking, the sender pulls the line low for 1 bit. That's the start bit. The receiver sees that drop and goes, "Okay, something's coming," and starts its timer. It then reads the 8 data bits at that speed they agreed on. Sometimes there's an extra parity bit just for a quick error check, and then finally the line goes back high for the stop bit. That tells the receiver the message is over. Every single byte gets this special treatment.
And if you're using an Arduino, this is all made incredibly easy for you. Serial.begin is what you use to set up the connection and agree on that all-important speed. Serial.print and printline are how you send stuff out. Then, on the other end, serial.available is like asking, "Hey, got anything for me?" And serial.read is how you actually grab the incoming data. It's a really intuitive way to handle that phone call.
But what if you need more than just a one-on-one call? What if your microcontroller needs to juggle conversations with, like, a dozen different sensors at once? Well, running separate UART lines for each would be a nightmare. That's where our next protocol, I²C, is a lifesaver. Think of it less like a phone call and more like a perfectly moderated conference call.
I²C, which stands for Inner Integrated Circuit, is just brilliant. It can connect a whole bunch of devices using only 2 wires. Seriously, just 2. You have SDA for the data and SCL for the clock. Now, unlike UART, this one is synchronous. That shared clock line acts like a metronome, keeping everyone perfectly in time. And here's the magic trick. Every single device on the line has its own unique 7-bit address. It's like giving everyone on the conference call a unique name, so the host can say, "Okay, Bob, it's your turn to talk," and everyone else stays quiet. And this slide right here shows you just how powerful that design is. You can have a whole collection of sensors, temperature, humidity, and accelerometer, you name it, all hooked up to the exact same 2 pins on your microcontroller. This simplifies your wiring like you wouldn't believe and saves a ton of your precious I/O pins. It's just a crazy efficient way to build a complex project.
So how does this moderated call actually work? Well, the master device, usually your microcontroller, kicks everything off by creating a special start condition on the line. Then it shouts out the 7-bit address of the specific slave it wants to talk to. Any slave on the line that recognizes its own address responds by pulling the data line low. That's called an acknowledge, or I²C. It's basically them saying, "Yep, that's me, I'm ready." After that, the master and that one slave can exchange data. And when they're all done, the master creates a stop condition to hang up the call and free up the line.
Now, UART is simple. I² is super efficient for connecting lots of devices. But what if you just need raw, blistering speed? What if you're trying to read from an SD card or drive a big, colorful display? For that, my friends, we enter the fast lane with SPI. This is less like a conference call and more like a highly structured, super efficient board meeting. SPI, or Serial Peripheral Interface, is built for one thing: speed. It's synchronous, so just like I²C, it has a clock line to keep things tidy, but its real claim to fame is that it's full duplex. And that just means the master and the slave can talk and listen at the exact same time on different wires. That can basically double your data speed. To pull off that full duplex speed, SPI usually uses 4 wires. Now, I should point out, the sensor in this picture actually uses its own unique single-wire protocol, which just goes to show you how many different methods are out there. But if we were connecting a standard SPI device, we'd use these 4 lines. We have SCK, the clock. We have MOSI, master out, slave in. That's the data line from the master to the slave. Then there's MISO, master in, slave out, which brings data back from the slave. And finally, SS, or slave select. The master uses this line to tell one specific slave, "Hey you, I'm talking to you now."
One last quick thing on SPI. It can get a little tricky because there are 4 different modes. This table looks complicated, but it all just comes down to timing details, like, is the clock normally high or low, and do you read the data on the rising or falling edge of the clock pulse? The good news is you don't need to memorize this. You just need to look at the data sheet for whatever sensor or device you're using and make sure your microcontroller is set to the same mode. Okay, we've learned the languages. We know about the simple phone call of UART, the busy conference call of I²C, and the high-speed board meeting of SPI. So now let's put this theory into practice. Let's see how we use these protocols to connect our microcontroller to the real world. Let's give our little brains some senses. These protocols are really just the bridge between the clean digital world of ones and zeros inside the microcontroller and the messy analog world that we all live in. They let us hook up to this incredible universe of sensors that can see, hear, and feel things our code just can't on its own. So first up, we have the classic HC-SR04 ultrasonic sensor. This thing is basically sonar for your microcontroller. It has a little speaker that sends out a super high-frequency chirp of sound, which travels out, bounces off an object, and then comes back as an echo to a little microphone. Your microcontroller just has to measure the time it took for that round trip. Since we know the speed of sound, a little bit of math gives you the exact distance. And what's interesting is how it communicates. It's super simple. You just send a pulse to a trig pin to make it chirp, and then listen for a return pulse on an echo pin. So it doesn't even use UART or I²C, which shows that sometimes, for simple jobs, a basic digital signal is all you need. Next up is the PIR sensor, which stands for passive infrared, and the key word there is passive. It's not sending anything out like the sonar sensor. It's just watching. It's looking for changes in infrared light, which is basically the heat that you and I and other warm bodies give off. Inside, it has 2 little sensing elements. When a person walks by, they create a change first in one element, then the other, and that difference creates a very specific electrical signal. And just like the ultrasonic sensor, the communication here is as simple as it gets. The output pin just goes high when it sees motion and low when it doesn't. It's a binary yes or no answer. And finally, let's look at a true classic, the LM35 temperature sensor. Now this one's different. It's an analog peripheral. It doesn't speak in the digital ones and zeros of our protocols. Instead, it just puts out a constantly changing voltage. The really clever part is that the voltage is directly proportional to the temperature in Celsius. For every degree, the voltage goes up by 10 millivolts. So if your Arduino reads 250 millivolts from this sensor, you know with certainty that the temperature is exactly 25 degrees Celsius. It's a great contrast because while the LM35 is simple, a lot of modern, fancier sensors that measure temperature, humidity, and pressure all in one will use I²C to send all that rich data back to the microcontroller. And there you have it. We've gone from the basic idea of sending one bit at a time all the way to understanding the languages of UART, I²C, and SPI. We've seen how these tools let us connect our isolated little brain to sensors that give it eyes, ears, and a sense of touch. These protocols are your key to building smarter, more interactive projects. So the only real question left is, now that you know how to make your microcontroller sense the world, what are you going to build with it?